who do not know me, my name is Sayak. I work at Face. I work on things like diffusers, TensorFlow, and computer vision. Yeah, this is sort of my brief bio, and I think that's enough of the work. I like to binge watch things on Netflix. Currently, I'm binge watching Outer Banks. It's a fairly old series. And if you ever wanted to know more details, you can go to sayak.dev. And you will be able to find all of the things that I've made public so far. So yeah, that's about it. And this is a disclaimer. Although the title might sound very blunt, I do mean it in a very humorous manner. If I hurt anyone's sentiment, I do sincerely apologize for it. But know that it's purely for humorous purposes, and it's not to hurt anyone's sentiment. And that's the only moment of time I will be standing. Now I'm going to say. And you do not have to write anything. I'm going to share all of my slides so that you can focus or do talk to me. These are the things I want to cover. A few aspects of, by the way, before I start, how many of you use TensorFlow in your day-to-day life? How many of you have heard the word called TensorFlow? I'm not going to introduce what TensorFlow is. I think TensorFlow.org, the website, does a fairly good job regarding that. In this, and also this is not a session for absolute beginners. I think this session is very useful for folks who have got an intermediate amount of experience using TensorFlow. So also do not fret if you do not understand something. Just feel free to stop me at any point in time and ask, okay, Sayak, I do not understand this. Would you care to explain? And yeah, I'll try my best. So I want to cover these things, a few aspects of TensorFlow that I find to be either underappreciated or underused, but are useful to know. And I want to also shed some light into the situations. Could you please all make your phone silent? I think I really appreciate it. And also some of the situations where these things are really useful. So let's get started. First point. So you folks, some of you folks predicted it right. I will cover XLA, but that's part 2 of my talk, where I'll cover XLA, how you can sort of speed up your TensorFlow programs up to 100x. But first, I want to cover a very basic thing: how do you handle variables and sequences in TensorFlow? And for the ones that work in natural language processing domain, I think handling variables and sequences is something that you deal with on a day-to-day basis, and it's also a very fundamental thing to think about. So yeah, what do I mean by variables and sequences? These are variables and sequences. Why they are variables and sequences? Tell me.
Length differs.
Fair enough. Length differs. How do we measure the length of a sequence?
By the number of words.
We'll settle with number of words. You can also count the number of characters, but we'll just split the sentence and we'll take the words out of the split. So the first sentence contains 5 words, and of course, yeah, I'm an excellent person, but I do not play cricket. That's a sarcastic one. So of course, these are variables and sequences, and now to work with these text sequences, these things need to be represented as numbers. Computers do not understand, natural language words. They need to be, represented as numbers, so our computers can take them as inputs. And they also need to be pre-processed to some extent to discard some unnecessary stuff. And what do I mean by unnecessary stuff? That's not needed for the purpose of this session. Basically, you can think of if I have a text sequence called I am an excellent person because I do not play cricket. In order to make your computer take that sequence as an input, you need to sort of convert that to a numeric representation. And the numeric representation would look something like this. And the sequence length here is 10 because the sequence contains 10 words. Clear? Any problem? Cool. And we all are here because of neural nets, because why not? And in order to train your neural networks with these, pre-processed sequences like numeric representations, you need to batch them together so that you can perform something called mini batch SGD, which stands for stochastic gradient descent. Of course, there's add-on and something, but yeah, I will settle with SGD for now. You need to batch this similar, batch these sequences together to train your neural networks using mini batch SGD. And then the last point is the most important one. For batching the sequences in a particular batch need to be of uniform shape. So what I mean by that is, let's say you want to form a batch of sequences. You want to form a batch with these sequences. Now you cannot actually form that batch because these sequences have variable length. Cool? In order to batch them together, they need to somehow be constructed in a way so that they have uniform sequence length. Like the first sequence will have 10, the second sequence will have a sequence length of 10 and so on, but you are free to decide on any particular sequence length. But yeah, I just wanted to give you an idea. It could be 5, it could be 6, it could be 10, it could be 11 or something, but the very idea is for you to collate these sequences in a batch, they need to be of uniform sequence length. That's the idea. Any doubts? Clear. Cool. So batching option 1. On the left hand side, I have a batch of sequences and the cells denote their sequence lengths. Cool. And you can see all of them have different sequence lengths. Cool. On the right hand side, what I'm doing is I'm creating mini batches out of the pool of sequences that I have, and I'm padding all the sequences to a uniform sequence length. Cool? Yeah? Any doubts? You see all the batches, all the sequences in all the batches are being padded to a global fixed sequence length. Cool? Now consider this part. And now notice the differences in between the two. What's the difference?
The batches are padded in the first one.
Sorry?
We are using extra padding in the first one.
You'll have to do better than that. Notice carefully.
What is the yellow sequence,
Sorry?
What is the yellow?
That's the padding bit.
Same max length across all the batches.
Same max length across all the batches where? In the first
For the
one.
first one, second one is variable. Based on
No, it's
the
not variable. It's actually batching it, and in the batch, the maximum sequence is being padded to.
Yeah.
taking the length of
So in the right hand side, what we are doing is we are taking the maximum sequence length of the sequence present in the batch. So the maximum sequence length bit is not fixed. We are first calculating what's the maximum sequence length for a batch of sequences, and then we are using that value to do the padding. You see, for the first batch, we are already saving one padding bit, isn't it so? Isn't it so? And padding means basically a bunch of zeros. And if we can reduce that one padding bit, what does that mean? We are basically saving on some compute.
Yes.
Because zero computation is zero computation. There is no other way to say it. Cool? Clear? Any problems?
If the data is not sequential, we can even sort it so that the start.
I have already said that. How do we do variable and sequences? I have already made that clear enough.
Right? No, I was just saying, if we sort it, we will save even more bits by.
Yeah, if you sort it, the network will learn to adapt the sorted pattern. No? During training you can't sort. During inference you can actually sort. Because if you sort it during training, the network will somehow try to pick that sorting pattern. This is why actually during inference you picked up on a really good point. During inference we sort it to save some further compute, but during training we do not sort. Cool. But anyway, the idea remains pretty simple. Instead of padding with some predefined global sequence length, we pick the maximum length sequence from a particular batch, and we use that value to pad a batch of sequences. Clear up to this bit?
Yeah.
Cool. And again, let's revisit this. Sequences in a batch, shorter sequences need to be padded and longer sequences need to be truncated. Cool? But shorter or longer than what? Exactly what? Consider these two things. Length of a given sequence, shorter or longer than some fixed global value, let's say 128, sequence length is 128, and length of a given sequence shorter than the maximum sequence length of a batch. Basically, these two things represent these two. Like on the LHS side, we have some global fixed sequence length, let's say 128, On the right hand side, instead what we are doing is we are picking the largest sequence length in a particular batch, we are computing its sequence length and we are using it to pad all the other sequences present in a particular batch, but not for all the other sequences present. Cool? Abundantly clear? Cool. But again, before we do hands-on, let's consider this scenario. Let's say we have a data set of text sequences where the maximum sequence length is 1829. That's a lot of words. Lot of words. 1829. In the age of WhatsApp, that's a lot of words. Basically, in the age of Twitter, that's a lot of words. Minimum sequence length is 6. That's too low, no? And 50% of the sequences in your data set have the sequence length of 79. That's fairly okay. 75% sequences have 1-to-1 sequence length. Cool, you have the statistical part clear. Now my question is, does it make sense to pad all the sequences to the length of 1829? Does it make sense? If you say yes, then we have a problem. Then we will have to settle with some convex codes. You don't have a problem with that, right? 1829 can't be the way to do it. Cool? Cool, we all agree? Cool. Oh, sorry. This is what happens when you do too much LLMs. No offense. So, cause why not? Talk is cheap, shown there. Let's see how well we can scale this up and what are the benefits of using batch-wise maximum sequence length to do our padding. This is way too large. Let me zoom out a bit. Okay, cool. Let's start. I'm gonna have to use a GPU here. Change runtime type, but I have access to a pre-training plus GPU. That's cool. Let's see what GPU I'm using. Alright. These things take 1-2 minutes of time. Might take 1-2 minutes of time. So that's fine. So basically, in the code section of my talk, I'm gonna show you how to use batch-wise maximum, the concept of batch-wise maximum sequence length in order to do the padding and truncation thing, and what benefits do we have if we use it. So basically, I have an IMD genre classification problem. Where the idea is to predict the genre of a movie from its title and descriptions. It's a pretty simple multi-class classification problem, but good enough to demonstrate what I'm trying to teach. I have got access to an A100, so that should be pretty cool. These are basic stuff, data visualization and all that. But yeah, let's figure out something. Let's see some info on the sequences. What? Oh. It's loading the data set. Okay, cool. So basically, I'm getting some info on the summary of the movies that I have. Getting some info regarding their sequence length. So the maximum sequence length here is 1829, and as we discussed, it does not make sense to pad to this sequence length. So let's see, how to do it in the right way. Cool. So what I have is, I am first initializing a text vectorization layer, which under the hood does TFUG vectorization, and then I have a string lookup class which basically encodes your string class labels. But yeah, let me show you how the labels look like. You basically have a summary like this. Listening into a conversation between that sort of stuff. Basically, the summary of the movie, and then you have the genre. It was a drama, it was a thriller, it was a narrative movie, or something like that. So the text vectorization layer will basically take a summary, a movie summary. It will apply something called TFUG vectorizer, and then it will give you a numeric representation of that summary. And string lookup, what it will do is it will convert the genre, let's say drama or adult or thriller. It will give you a single integer class level, something like 0, 1 or 2. because computers do not understand text sequences. So that's about it. You do not need to know all the body details, but at this point in time, things are clear. Any problem? Cool. Now, what I am doing here is, this is the important bit. When you are initializing the text vectorization layer, either you have the option to specify the output sequence length. You can specify it to none, or you can settle with some predefined value, 128 or 512 or something like that. But again, I have conditioned this particular method on the padding length. I have the option to specify it to none, or I can specify it to some predetermined number, 128 or 512 or something like that.
Like the output sequence length is the global.
Yeah, so you can either specify it to your choosing. It can be some global output sequence length, it can be 128, it can be 512 or something like that, or you can choose to specify it to none. So yeah. So let's see. Here, as you can see, I am specifying it to none, which means all the output sequences will be just present in their numeric forms. It will not be padded. That's the most important bit. It will not be padded. The output sequences will not be padded to some predetermined sequence length. If you specify padding length to be none. Cool? Alright. Let's prepare the data sets. Cool. Now here's another important bit. The bit about how I am making use of the batch function. You see, here I have my preprocessing function which takes care of converting the textual sequences and the class labels into their numeric forms, and then I am either using dot batch or I am using padded batch. Alright? And I am gonna come to the differences between the two, but for now just keep this in mind. I can either use dot batch or I can use padded batch. Cool? Now for the first bit, we are not using any predetermined sequence length for padding or transition. Which means padded batch is gonna get called, as we can see from the function itself. If padding length is specified, then batch is gonna get called. Otherwise, padded batch is gonna get called. Which means here padded batch is getting called. Cool? Now I have prepared all the batches and stuff. Let's see the maximum sequence lengths across all the different batches. You see they are varying. So our intuition was kind of correct. You see the variance in the sequence lengths across the batches, they vary crazy. Like some of them have 1800, some of them have 800. Like orders of magnitude lower sequence length across batches. No? Cool. Clear up to this point?
Yeah.
Cool. Now let's go to GPT-5 model. So we have our GPT-5 here, which can predict, which can take as an input.
Yes.
Oh sorry, this is not a GPT-5. Sorry. This is a simple bidirectional model. Sorry. It can take as an input a movie summary, and it can tell you the genre of the movie summary, whether it's drama or adult or thriller or something. So cool. Let's initialize this. We are gonna, for reproducibility purposes, we are also gonna save the initial weights, and let's train this thing for 5 epochs. Cool. Alright. It's gonna take some time because real schemes are bad. It takes very long amount of time. So yeah. But yeah, I have already pre-trained it so that we do not have to waste the time. So the total training time to train this GPT-5 model, world's largest model so far, it takes about 149 seconds. 149 seconds. Okay, on an A100, which is a fairly modern GPU, and this is a lot. This does not matter. So all that matters is we have 149 seconds. If we do variable length batching, cool. If we follow the approach of variable length sequence length thing, the one that we just discussed, where we take the maximum sequence length of a batch to do the padding thing. If we do that, then our GPT-5 model takes 149 seconds. Clear up to this point?
Yep.
Now what we are gonna do is, we are gonna do the opposite thing. We are gonna set it to the maximum sequence length, 1829. Cool? What happens is, now you have 297 seconds to train the GPT-5 model for 5 hours. Cool? And you see the loss, the loss thing. Let's revisit the previous loss one. You have a diode kind of thing, diode kind of a loss curve. So, and the diode pattern still remains the same, but the timing has got increased quite a lot, no? Cool. That's about it. Now the ones that wants to train less modern networks like BERT, Robota or something like that, less modern, sorry. You can definitely check out this blog post where we go really deeper into TF.ragged tensors, something that I wanted to cover today, but I cannot because ragged tensors are ragged tensors. They are basically jagged, not ragged. So you are welcome. You are definitely welcome to check out this repository again. I'm going to share the collab notebooks and all that so that you can refer to them whenever it's needed. So that's about it. So let me go back to my slides and just proceed. So reduced timing, we all have seen that. It does not take, it reduces the time. If we do the batch-wise maximum sequence length thing, if we make use of TF.padded batch in a clever manner, then it can actually reduce your training time, but it still keeps the training landscape same, so that's good. And of course, you would want to impress your supervisor, right? And earn that next thing that you were looking for. So go ahead.
Instead of taking max, if you would have fixed it to 128 or some fixed length, what would have happened?
Then information might have got lost. No?
We
I
might not
could
be-
have used 32 as well.
Might not be able to predict the genre correctly.
Yeah. Information might get lost because if you have, let's say, a sequence whose sequence length is 128 and if you pad it to 32, then you are missing out on a lot of context. Cool?
75%
That thing might have worked, but again, deep learning is more algorithm than science. You will have to run experiments. That previous statement is by Frankfurt, it's not my business. You will have to run experiments, but in general, if you do batch-wise maximum thing, you get based from both the worlds. You do not have that palpitation. Hey, I'm missing out on a lot of context. You don't have that palpitation, but still you are able to reduce the training time, and of course impress your supervisor. Running TensorFlow programs fast. Now this is where I would definitely want you to get excited because we are about to speed up our TensorFlow programs by 100x. And if that does not excite you, then definitely we have got a problem. Either I am not in my right mindset or you are not in your right mindset. We need to settle that bit. Cool. Let's go. All right. Let's cut to the chase. This is GPT-6, by the way. It can generate anything basically. It can also generate Sayak 0.2 and whatnot. Basically, what I wanted to say is GPT-6. This is a TensorFlow program. The model thing, the red highlighted thing. This is a TensorFlow program. Like you have a C++ program, you have a C program, but TensorFlow is like so legendary and so seminal. We call it TensorFlow program. But this is just a program. Let's say this is a TensorFlow program. The model is TensorFlow program. And GPT-7 it's also a TensorFlow program. Yeah? Cool? This model underscore span, which represents the entire chronology of GPT-7, it's also a TensorFlow program. Alright? Cool. Now, with that in mind, I want to give you an LI5, and for those who do not know what LI5 is, Horitro, what is LI5?
Explain me like I'm 5.
5 years old. 5 years old, not 5 feet. 5 years. So, like, I want to give you a very basic introduction on operated fusion. What I mean by that is GPT-7 and GPT-6. Yeah, both these things need memory access and compute. When you have a program or a function that does some stuff, let's say multiplication or division or subtraction or addition, it needs to access memory to store the variables. X is a variable, y is a x equals to y plus z. X is a variable, y is a variable, z is a variable, and it then needs to compute stuff. What is the computation that we are performing in x equals to y plus 7? What is the computation? Y plus z. What's the computation? It's an addition, and x equals to, it's an assignment computation. Cool. There are two computations involved, and then we need to store the variables, the x variable somewhere, and that relates to memory access. Cool. Clear what do we mean by memory access and compute? The computer needs to go somewhere in deep down its registers and store that variable called x. Cool. Like remember your C programs where you need to access some variable with pointers and so on. Cool. You need to perform memory access and then you need to perform the computation bit. Cool. And if you do memory accesses too much, you can actually make the execution time of a program costly. Let's say you need to go to a register, then come back, do the computation, then you need to visit another register, go back and do the computation. There's a lot of back and forth, no? It's like you're going to school, then you are coming back to your home to pick up something, then again, your relationship life will get. I don't know. So, I mean, you understand how too many memory accesses can make the execution time of a program costly. Intuitively, you can think about it, right? If I need to access memory too frequently, it can be costly. It can lead to costly outcomes. Cool? All right. Now, this is the perfect example of how things can be optimized if you reduce the number of memory accesses needed in order to do some computation. On the left hand side, you go back this way, then you go back another way, and then you do lots of back and forth. And on the right hand side, there's just one memory access. And that's how you actually optimize the computation of radio, which is the best activation function in the world. Cool. No, I'm not opening it up for arguments. Radio is the best activation. So yeah, on the left hand side we have too many memory accesses, and on the right hand side we have the same amount of compute but only 2 memory accesses. Cool. And that immediately optimizes your program. It immediately reduces the total execution time of your program. Cool. And this is the very idea of fusion. If we can fuse operations, they would likely run faster because we are reducing their memory operations, which means we are increasing the amount of compute intensity. And that's exactly where the notion of speed up comes from. And of course, neural networks are just about multiplications and basic mathematical operations. So of course, the idea can be extended to neural nets as well. And in your head, you might be thinking, do I need to again go back to C? Can't I settle with Python only? Do I need to know pointers and all that? So of course, I'm going to show you how. But what fun, without a little drama. So allow me to introduce XLA. I'm going to shamelessly read out whatever the official documentation says. XLA, Accelerated Linear Algebra, is a domain-specific compiler for linear algebra that can accelerate TensorFlow models with potentially no source code change. That's the most important thing, because we do not want to go back to CPP or C. So yeah, and here's the summary. XLA can help run your TensorFlow program faster, both in terms of memory and speed. And the teaser, text generation can be 100x faster if you do XLA, and I'm going to show you how. Because you do not have to take my words for granted. Code is your source of truth. And the reason why I wanted to briefly introduce the notion of fusion is because, amongst other things such as styling, which is not important for the purpose of this session, fusion is XLA's most important optimization. So even if you intuitively understand what operator fusion means, you basically know 75% of XLA. All the optimizations that are happening under the hood. At least you know them intuitively. I'm not saying you know them technically to their body details, but you at least understand them infinitely. I think that's very important. And this is like the flow chart of how XLA handles the optimizations. It has a few target independent optimizations like common sub-expression elimination and so on. And then, yeah, of course, why not? First, it does target independent optimizations and analysis, for example, common sub-expression elimination and so on, which are not device dependent. And then, based on the device that you are using, whether it's a CPU or it's a GPU or it's a TPU or some any other hardware accelerator, it performs some target dependent optimization, like kernel density and so on. The target dependent optimization bit, you can forget about it easily. But the target independent optimizations, they actually include the operator fusion, the tiling thing, common sub-expression elimination and so on. Expressions that basically make your computation redundant, like +1 or +0 or x equals to x plus something or something like that. Those sort of stuff. So cool. Now let's see. Now again, let me go back to some GPT next. Again, consider GPT-8. We have already made it to GPT-8. So yeah, GPT-8. And then even if you just trace it, in TensorFlow there's a notion of tracing. Even if you just trace a function, just trace it, like figure out what the computations are, what the data types of the variables are. If you just do that, you get certain amount of speed up. Like GPT-8 in its native form takes 2.429 seconds to run on a CPU, and if you just trace GPT-8, it takes 0.14. If you just do this, if you just add the TF.function decorator, it immediately optimizes your code without any bells and whistles. Cool? Again, a means to impress your supervisor and earn that promotion. So yeah, from 2.429 to 146, but you would want to go higher up the ladder. Cool? Now this is where XLA comes into the picture. So we go further down the next step. Earlier we had added TF.function to GPT-8, to native GPT-8. Now, apart from adding TF.function, we also specify here also XLA compiling, which means JIT compiling. Cool. Now JIT compiled GPT-8 takes 0.03. From 0.14, we are now down to 0.03. If it does not excite you, I am not sure what to do. So we started off with 2.42, then we went to 0.14, then we are on to 0.03. Claim all the praises that you want from your supervisor. So, yeah, and it's just one line of code change. You just specify G compile true, and you add that TF.function decorator and done. Magic. PC shortcut. Okay. Now GPT takes 0.03 seconds. Hey, open your laptops and chat it. So XLA compilation is possible for arbitrary function. It's an arbitrary function. GPT is basically arbitrary. It's addition and multiplication. Nothing else. Cool. Now my question is, XLA compilation of arbitrary function, that's possible. What about my models? MobileNet V3 large. If you load it with our favorite TF.ks.application, and then if you call compile and specify JIT compiles equals to true, 59% speed up. I'm gonna show you the code. So of course, hold your horses. And then if you do it in the native way, if you can compile the function, if you trace the function first, the MobileNet function, because remember, model is also a TensorFlow program. It's not just a model, but it's also a TensorFlow program at the end of the day. If you trace it and then if you XLA compile it, 98% speed up. I'm gonna at least claim $10,000 in my case. I'm not settling with anything else. 98% speed up with just one line of code change. Cool. I'm gonna get that sink in. Because talk is cheap, show me the code, and here's your code. Alright, I'm going to disconnect this runtime because I do not need it anymore. Disconnect and delete. And read, and I'm gonna connect to another runtime, make sure I have got access to a GPU. I have got access to a GPU. That's cool. This is the boring stuff where I basically show how XLA can be used in order to speed up the training process. You can try it for yourself because I'm gonna share the collab notebooks. I very much encourage you to play with these notebooks anyway. So I'm gonna skip to the more interesting bits. Let's start from here. Yeah, run anyway, and let's see if the speed ups are actually real or these are some jacked up numbers. So let's wait for a minute while it gets initialized, and then we will on over it. Yeah, that's fine. Everything is imported, hopefully. So we have the same functions from our slides. One where we are just tracing, and then we are also not just tracing, we are also JIT compiling it. So cool. Now we have our functions. Let's run them. And see. You have the results. Takes 7 seconds. The next one, traced function takes 0.22. JIT compile one takes 0.01. You have the results with you. You have the code with you. Now you just need to get hands on. Now let's also see how actual models turn up, because GPT-8 is probably not going to be that useful. We would want to use more advanced models. So let's load mobile network 3 large, and let's calculate the error runtime. It takes 0.6329 seconds. Cool, not bad, not bad. Now we are compiling it, but with the XLF flag set to true. It takes 0.61. So from 0.63 it gets to 0.61. Not very impressive though. 0.63 and 0.61. It's very minor. Nah, that's too bad. Now let's see what happens if we do it in the native way. We first trace it and then we JIT compile it. 0.06 is what we do. This is magic. So I'm kind of sure even I myself do not use XLA to an extent where I should be using it. So I encourage all of you to go back and study the documentation of XLA and figure out how you can speed up your TensorFlow programs, because this speed up basically comes for free. Almost comes for free. That's in brackets. Almost comes for free. Now, before I actually conclude my talk, I have just one final bit to share with you all, and that is, let's go back to the slides first, and let's see. Now, as I mentioned, we can use XLA for training loops as well, and here are some links which you can further study in order to see how you can actually benefit from using XLA in your training loops as well, and the speed up can be orders of magnitude faster actually. Now this is the bit where I'm most excited about, that is text generation. In its native format it's very slow, because in text generation you are starting with some starting token, and then you are predicting the next token, and then you are taking the starting token and the predicted token, and then you are predicting the another token. It's like very auto-regressive, and it's very sequential and iterative in nature. So by definition of the problem, text generation seems like a very computationally expensive affair. So this is where XLA can be really powerful, and I'm gonna show how you can speed up your text generation workflows by 100x faster. So cool. Let's open up this notebook. So I'm installing a library called Transformers. It's maintained by the organization I work for, Hugging Face. So I think last year around August, we had to write we decided to write most of our text generation models in TensorFlow to be natively XLA compatible, because in order to make models XLA compatible, you need to take care of certain bits. Those bits are not very important, but I'm going to discuss them in a moment. And after we made all our text generation models in TensorFlow to be natively XLA compatible, we were able to observe 100x speed up. So let's actually see them, because talk is cheap. Show me the code. So I'll let it install. I'm going to ensure I have access to the GPU. Oh no. We can't proceed. We need access to a GPU. Alright. We'll have to do it again. But that's fine. It does not take much to run. So I'm going to install it again. And yeah, while that's shutting up, let's discuss this code. So basically, before you pass your prompts or start tokens to your text generation model, you basically need to tokenize your initial prompt or initial signal. You first need to tokenize it, and that's why we are loading a tokenizer, and then we are also loading a sequence language model, and then we are specifying some arguments which is fine for the session to get ignored, and then we are basically doing this. So this code should be familiar to you already, because we are basically first tracing the text generation function from the model, and then we are JIT compiling it, which is what we were discussing in the earlier slides. So this should seem familiar. And we are using a model called T5, which is a sequence-to-sequence language model. And another important bit that you should know is that you should specify this pad to multiple of things, because you would want to pad your sequences to a uniform sequence length. Like if your model was compiled, if your model was JIT compiled using a sequence length of 32, then you should always be using that sequence length. Now if you pass a sequence length of 128, then your model will trigger recompilation, and it will end up in a ridiculously increased amount of generation time. So that's an important bit to remember. Just remember to use the same sequence length with which your model was originally compiled, and make sure to use that throughout, because otherwise it's gonna trigger retracing, which is gonna end up in increased amount of text generation. So that's the only important bit to remember. Oh, blame Joao Gandhi. It's not my fault. Sorry.
Done.
Alright, this is the most important bit, not the comments, but this one. Back to my So this is basically very self-explanatory stuff. We want to return the tensors in the TensorFlow format. TF means TensorFlow by the way. Padding, we are interested in padding the sequences, and we are interested to pad them to the multiple of 32. And number of means maximum new tokens, I do not understand those, so I'm going to skip those. So yeah, and then once we have initialized our T5 small model, it's not GPT-9 yet. We are going to have to settle with T5 small, no GPT-9. So we are going to compile the function that's responsible for generating new tokens into XLA, and then let's kick this process off. Let's see. Cool. It's gonna do some stuff under the hood, but the only thing it's first downloading the model weights. Otherwise, the model is gonna predict garbage, which is not something we are interested in. We can safely ignore all the warnings because they are not important. the TF models are getting downloaded. As we can see, downloading TF underscore model.h file will be only a couple of minutes. All we are interested in this original prompt, generated prompt, and the execution time. So let's go. Let's see what happens. And the warnings are safe to be known, so don't worry about it. And of course, the first time you use your XLA compiled model, it's gonna figure out how to best infer the graph, and then you are gonna notice a speed up. So the first execution time will always be high because it's inferring the graph, it's figuring out how to best dispatch your model operations through the most optimized kernels. That's why it takes way larger amount of time. As you can see, it takes 24095.1 milliseconds in the first iteration, and you can see for yourself. The next iteration takes 26 milliseconds. Like 2 orders of magnitude lower. If this does not excite you, I honestly do not know what will.
1,000.
And sorry?
1,000 times.
Yeah, so why not use XLA in the first place? I'm sure XLA is definitely not used to the extent it should be. So now we are back to GPT-2 again. We are traveling back in time, back propagation through time, such a cool word. So GPT-2, let's take GPT-2. Finally, not GPT-10 but GPT-2. Cool. And the arguments still remain the same. We would want to pack to a multiple of a certain value and not use variable values here. And then we are first loading the corresponding tokenizer of GPT-2, and then we are also loading the model. By the way, GPT-2 is an auto-regressive model or causal language model. It's not a sequence model. That's why we are using a different class to load this model. And the rest of the things remain the same. We are using the same tf.function and compile thing to XLA compile our generation function, and let's see the amount of speed up that we can get. Again, the TF model weights are gonna get downloaded. The first iteration will always be orders of magnitude higher, and then we should expect to see a certain, not a certain, but a significant amount of speed up in the generation speed. So let's see. Model weights are getting downloaded. GPT-2 is higher, it's heavier than GPT-5 small. Warnings can be safely ignored. It's not a problem. Yeah. So 2 to 6 to 4.4 milliseconds first iteration. Second iteration is 81.4. Third iteration is 78.2. This is black magic. I don't know. But the point I wanted to raise is XLA again. It's a pretty generic thing. I used XLA to optimize stable diffusion models by up to 25% the image generation speed. So I really encourage you to dig deeper into the Excel documentation and see how you can speed up your TensorFlow programs if you are not doing that already. And again, let's get back to the slides. Let's get back to the boring things. Thoughts on Excel, because these are important bits to consider. We didn't actually even scratch the surface of Excel, but I really wanted to give a taste of this powerful compiler, which again, as at this point in time, I think it should be very evident. I wanted to give you a taste because I feel it should be more used. And when used right, as we saw, gains with XLA can be huge. And you should be aware of a couple of gotchas if you wanted to make your TensorFlow programs to be natively XLA compatible. There are lots of gotchas in fact, and if you can take care of them, the gains with XLA can be huge. And there's a learning curve. XLA is not that easy to get from the get-go. It has a steep learning curve, so I definitely suggest you to accept that learning curve and go for the higher outcomes. And Of course, you might want to argue if I had target dependent optimizations in mind, we could have also settled with things like TensorRT or TensorFlow Lite. But again, XLA is like it comes with your TensorFlow installation. It's a native thing supported by the TensorFlow ecosystem, so why not take advantage of it? And of course, this is a diffusion generated image, and if you want to get access to the resources, scan it out, do whatever, note it down. All my materials are there, the slides and the code that we discussed, everything is there. It will basically take you to this repository where I have basically included everything. And if you want to click pictures or something, I'm gonna show this slide for 20 more seconds and then I'm gonna hop off. So that's about it.
That is your public paper, right, Peter?
Of course, let me double check.
No?
That's it. Alright, that's about it. Thank you, folks.